Hello guys, I welcome you all for the today's video. So today's video is all about the various instruction sets of ARM controller. Before moving further, let me introduce myself. I'm Lakshmi Vaibhavi NV, currently pursuing BE in CSE AI at SVCE. Coming into the contents, first topic is about what are instruction sets, types of instruction sets, examples of instruction sets, benefits of understanding the instruction set. So let me see about what are the instruction set. The instruction set architecture is fundamental for building fast, efficient computers that optimize memory and processing resources. It also specifies instructions, data types, processor registers, main memory hardware, input or output model, and addressing modes. The classification is a RISC and CISC in instruction set architecture. RISC basically it comprises the types of instruction set architecture that emphasizes simple instructions and a small number of addressing mode. That is, RISC emphasizes on software. The instructions of the same set with few formats uses more registers, fewer addressing modes, and complexity is more in RISC, and instruction takes one cycle at a time. Then pipelining is easier as we compare with the CISC. CISC is a complex instruction set computing is a type of instruction set architecture that emphasizes complex instructions and a large number of addressing modes. So CISC emphasizes on hardware, multiple instruction sizes and formats, less registers, then more addressing modes, extensive uses in microprogramming, and pipelining is difficult as we compare with the RISC. Coming to the classes of instructions, here we are with data processing instructions, branch instructions, load instructions, software interrupt instructions, and program status registers instructions. So let me deal with the data processing instructions. Data processing instructions. These are the fundamental arithmetic and logic operations of the processor and operates on the values in a general purpose registers or registers and an immediate value. Basically, these instructions manipulate data in the registers and memory location to produce the desired results. So, instruction is a task like what we assign for a processor to perform. If we give add instructions, it adds the two values in the registers and stores the result in the defined register or the destination registers. So before moving into the arithmetic register, let me tell you about the barrel shifter. A barrel shifter is a digital circuit that can shift the bits of a binary data or the binary number by a specified number of places without changing the order of the bits. It is commonly used in digital signal processing and microprocessor to design to perform arithmetic, logical, and data movement operations more efficiently. Here you can find the example. Logical shift right by 2. I had given the operation like it has to shift the value by 2 positions. See, it has been shifted over here, and this 2 value, the 2 MSB bits will be occupied by the zeros here, LSB. Actually, this barrel shifter will be used before any instructions proceedings. You can see the barrel shifter. This is the memory register from where barrel shifter acts. These results will be given to the arithmetical logical unit ALU, and the result from the ALU will be stored in the destination register. So let me get back to the arithmetic instructions. Arithmetic instructions are used for performing mathematical operations such as addition, subtraction, multiplication, and division. Here we goes with the syntax, instructions, conditions, and the suffix s and rd, destination register rn. This register is used to store the defined value. Here are the some mnemonics for the arithmetic instruction. ADC, add two 32-bit values and carry. Add two 32-bit value. RSP, reverse subtract of two 32-bit values. SBC, subtract with carry of two 32-bit values. SUB, subtract two 32-bit values. So here the example. As we know, add operations on 1 plus 1, the carry is 1 and a value 0 will be stored here. The same implies for the next value also. the carry is 1 plus 1, where the value of the carry is 1 and a 0 will be stored here. Next instruction is logical instruction. Logical instruction basically performs the logical operations such as AND, OR and XOR shifter instructions, which are used for shifting the bits of a data value either to left or right by one or more positions. Let me get into the example. Here I am performing the OR operations. You can see here OR, like perform OR operations between registers R2 and R1, where the value is stored in the destination register R0. Here the R1 value is 02040608. As we know, OR operation, if one of the value is true, like either one of the value is true, the total value will become true. The same things goes here. After performing the OR operations, this value is stored in a R0 register. So the final value is 1, 2, 3, 4, 5, 6, 7, 8. The mnemonics are AND, logical bitwise AND of 2-bit values, or logical bitwise OR of two 32-bit values. Then here logical exclusive OR of two 32-bit values, BIC logical bit clear value. It performs both AND and NOT operation here. Then comparison instruction. Basically the comparison instruction performs the subtraction over here. These instructions do not generate a result but set the condition code bits and set CV in the CPSR, set condition bits and set CV in CPSR, and often branches the operation follows to change the program flow. So as I said, the basic operation is subtraction over here. So here is the example. I am storing in R0 6 and in R1 6. When I compare the result, and when the subtraction here, there is no difference and the value is 0 here. So I am setting ZF is equals to 1 because R0 and R1 is containing the same value, that is 6. When I go with the second example, what I am here telling is, like, if two values in the registers are the same values, let me keep the mode as a user mode. The same thing happening here, comparing R0 and R9. Like R0 and R9 are 5 here, there is no difference and the user mode remains the same and the mode remains the same as in the user mode. Coming with the mnemonics are CMN, compare, negated means addition operations, CMP, subtraction, compare, TQ, test for equality of two 32-bit values, THT, test bits of 32 values, flag set has a result of Rn and N. Next, multiply instructions. This multiply instruction multiplies the values from the memory registers and source registers and places the least significant 32 bits of the result in the destination registers. This is for not, like, it doesn't specify what signed or unsigned bit over here in this syntax, but here we specify whether it is like the value should be either signed or unsigned value here. MLA multiply and accumulate, MUL just multiply, then this SMLAL signed multiply accumulate long, SUMLL signed multiply long, UMLAL assigned multiply accumulate long, UMULL assigned multiply long. Coming to the load and store instructions. This load and store instructions, let me tell you about the branching instructions. Branching instructions breaks in a sequential flow of instructions that processor is executing. Some other architecture call them jumps, but they are essentially the same thing. Here some of the mnemonics and the syntax I have given here. B, condition label, B stands for branching, BL branching with link, then BX branching with exchange. This is branching, exchange and with link. Link is this thing, a link register, like where the return address has been stored. Coming to the example here is the branch with link registers with link or BL instruction is similar to the branch instruction but overrides the link register LR with a return address. It performs a subroutine call. This example shows a simple fragment of code that branches to a subroutine using a BL instruction. To return from a subroutine, you copy the link register to the PC over here. The value will be given to the PC here. The branch exchange and a branch exchange will link are the third type of branch instructions. This BX instruction uses an absolute address stored in the register RM. It is primarily used to branch to and from the thumb code. Next, coming into the load and store instructions. Load and store instructions transfers the data between memory and the processor register. There are three types. So three types are, here we are with single register transfer, then multiple register transfer, and third thing is single register swap or atomic instruction for the semaphore. Coming to the example, so LDR and STR, here is the syntax for load store instructions. LDR, STR, LDRB means load byte into registers. Like we are specifying how much byte it has to be loaded. Then LDRH load half word, and here we specifying either like entire byte has to be stored or just a half word, or in that also whether like we have to store whether like unsigned or a signed byte into our registers. So example here, LDR and STR instructions can load the stored data on a boundary alignment that is same as the data type size being loaded or stored. LDR can load only 32-bit address, so and this must be a multiple of 4 bytes. As 32, it should be a multiples of 4 bytes. This example shows the load from the memory address contained in the register R1 followed by store back to the same register in the memory. So the first instruction loads the word from the address stored in the register R1 and places it into a register R0. And the second instruction STR, this also stores the values from the R1 and stores this values into the R0. Like it's storing the values R1 to the R0. Just here loading and storing happened. It doesn't perform any operations like addition, multiplication or any swapping. It won't happen here. They're just shifting the values in the load and store instructions. Next, coming into the software interrupt instructions. Software interrupt instructions are signals to send to the processor by software program to request specific services from the operating system or the other software components. These instructions allows programs to communicate with other parts of the system and perform tasks that require elevated privileges or access to the hardware resources. Here is the syntax SWI condition with a SWI number. SWI number is given in the vector table. You can refer to that. Here is the example. Before pre-processing, what are the instructions I am giving here is, in CPSR, the mode is in user mode. Then the PC contains with the value 00000800. Then link register, that is R14, which is defined earlier itself. 0 into 0, C, then remain F. Then this is called SWI number 1 2 3 4 5 6. Then after performing the SWI instruction here, usually this user mode will come into the shift to the supervisor mode, and the contents of the PC, that is program counter, will be given to the SPSR. Here you can also see the change in the mode. Mode has been shifted to user mode. When SWI is called in this, SWI is called, the SWI related instruction which is stored in the vector table will be given with the values of 0x00000008. Then the link register stores the return address 0x000804. So this is what basically happens here in the software interrupt instructions. Then moving on to the next instructions. This is the program status register instructions. This program status register instructions hold the information about the most recently performed ALU operation. Then controls the enabling and disabling of the interrupts, sets the processor operating mode. Here comes with the mnemonics MRS, copy program status register to general purpose registers. MSR, move a general purpose register to a program status registers. MSR move an intermediate value to the program status registers. So MRS, it's kind of similar. It's performs similar operations as we saw in the load store instructions. MRS instruction transfers the contents of either to the CPSR or SPSR into registers, and vice versa. Like MSR instruction transfers the contents of the registers into CPSR or SPSR. So this ends the instruction sets of ARM controller. So thank you guys for watching this video.